being error on the y-axis, on the z-axis, and x and y-axis are the two slope coefficients. What you see is any of the coefficient along this line will have the lowest value of error. Different, 1, 1, 2, 0, 0.5, 1.5. All of them will give you exactly the same error. So what you get in this picture of least squares is a ridge. Is a ridge that is there, a line that is formed. By adding that extra term, they call it as the regularization term. You know what it does? It penalizes you for having large coefficient, so that ridge get transformed into this nice parabola and you'll have a single minimum point. Let me ask you this. For this particular one, if in addition to the asking you to minimize error, if I ask you specifically, I want you to have these coefficients beta 1 and beta 2, beta 1 square plus beta 2 square should also be as low as possible. What value would you choose? What value will choose? Here beta 1 is 1, beta 2 is 1. Here beta 1 is 2, beta 2 is 0. Here it is 0.5, 1.5. All of them are possible solutions. But if I also add this condition that beta 1 square plus beta 2 square should be small, which one will work the best? This is 1 square plus 1 square, the summation is 2. This is 2 squared, so it's 4. This is large, this is bad. How about this? That will also be large. If I add this extra condition, then this will be the unique solution. This regularizes a problem which had infinite solution. It regularizes it and allows you to get only one solution. That's why this process is called as regularization. What it effectively does is it changes the minimization function that you are trying to minimize in such a way that you get a single answer, single value of answer. Now, coming to the question that you had, how do I know it actually minimizes the error in my test set? This process, how do we know whether it minimizes the error? We talked about this problem yesterday. Okay, we had the original problem was a sinusoidal curve, and I was trying to fit this sinusoidal curve by taking two train points at a time. Okay, so when I took these two train points, I got this line. These two train points, I got that line. I'm plotting a set of 100,000 different train sets. That's what I'm plotting. If without doing regularization, if I do least squares regression, this is the set of lines I'll get. Once I add regularization, I'm penalizing quantities with large slopes. When I do that, suddenly the range of lines that I'm going to get is reduced. The next plot that we did was the average of all of these lines and got the best fit line, right? And this over here was the variance of all of those lines together. The variance was 1.69. When I put regularization, the variance has decreased. It's 0.33. It's telling you that it will do better in unseen data, because trained data was only two data points. Rest of the data were all unseen data, and it does much better in the unseen data. So you are guaranteed that you are going to do generally better in unseen data. It might happen in the specific test set that you have. It's maybe not great, but generally speaking, in unseen data, this has a better chance of working than simple your least squares regression. This is one of the more powerful algorithms you guys will learn in this entire course. This concept of regularization can be applied no matter what algorithm you're talking about. There is neural networks with regularization. So neural networks is again trying to do very complex fit. Two neural networks, you can add regularization and insist that the coefficients need to be small. The regularized neural networks one works better on test data. You can talk about pretty much any of the complex algorithms that you're going to be learning and add this regularization term to that, and that ends up doing better in unseen data. Yeah.
So this regulation works like pretty well most of the time.
No, it doesn't take it by default. I don't have an answer for why it doesn't. I don't know. This is a more recent notion. This idea of regularization is a much more recent notion. The idea of least squares was done pretty much around the time of Newton. So it's very old. All right. Regularization probably is, I don't know, the idea of regularization was introduced in a slightly different, a purely mathematical world, maybe 100 years back. But for it being used in this context is probably 30, 40 years, not that old. So this is actually a very powerful technique, and it's not as prevalently used. But I don't have an answer for why they don't apply this regularly. Good point. It increases the bias. So it's not the least squares. What did least squares do? Least squares minimize the error in the train set. By adding this extra term, you are not going to minimize the error. The error is going to be slightly larger. But you don't care about error in your train set. On that, your variation on the test set is likely to be small by this. Your focus really is on the test set, and this is trying to address that particular thing. Now, there is no reason why we should try only this square of coefficients. Okay. Another way we could have done this, instead of doing square of coefficients, is putting absolute value of coefficient and say this is what I minimize. This kind of minimization has a name. The previous type of minimization was called as ridge regression. This is called as lasso regression or lasso regularization, which stands for least absolute shrinkage and selection operator. It's like, looks like they decided a name and tried to fit words to that particular name. I don't know why that came, but it has some meaning. You're trying to do absolute shrinkage, meaning you're trying to reduce the size of your problem set, size of your feature set. Okay, so that's where the term shrinkage comes from. Okay, so this is called lasso. The previous one was called ridge. Let me show you how this is implemented, perhaps after the break. Yeah, can we take a 5-minute break now? Yeah.
Yeah. So obviously a trade-off, and that's a call that we have to make.
There is absolutely a trade-off, and you depends on the value of lambda you choose. Based on the lambda, you are emphasizing simplicity more versus error reduction. And we will, the next few steps, we will talk about how you do this, how this play comes along. Yeah, let's take a quick break. We still have about half of the material left, so. Very hard to interpret. Is it too abstract? Okay. Yeah. Okay. Silence speaks volumes. Okay. I shouldn't ask questions for which I already know the answer, right? So here is the data set that we are going to be working on. It's a data set. The exact details of the data set is irrelevant. It's from a company analyzing different customers. It's a toy company. Depending on the number of children in the household, their favorite kind of game and all of it, they're trying to predict how much will revenue they spend, annual revenue they spend in that particular shop. Okay, so you have a whole bunch of features, and your target variable is revenue, total revenue that is being spent. That is the target variable. What we are going to do, we have loaded this particular data set, and we can do, and I mean, you're supposed to do all of this, study the data, look at the patterns in the data, find out which is the max, min, all of that you're supposed to do. I'm skipping all of that, going directly to the idea of the regularized regression for this. Okay, so one of the things is this is a data that has categorical variable. And just as we talked about in PCA, we need to convert all categorical variables into dummy variables and then start your analysis. So we are doing all of that, and we are creating train set and test set. I'm going to run all of that. So we have finally I have a train set and test set. GLMnet is the library. GLMnet is the library which contains regularized regression. Okay, so we are invoking that. So GLMnet, the way you call for this regularized regression, normal regression was just LM, right? Generalized linear models was GLM, right? This is regularized one. It comes under this command GLMnet. I'm training this. This is the train matrix. This is the Y variable I'm trying to train it to, and it allows in a parameter value alpha. When alpha is 0, it does ridge regression. What was ridge regression? Squares, beta square. That was the ridge regression. When alpha parameter is 1, it does lasso regression, which is absolute value of beta. Okay, and I'll show you what is the effect of each one of those regressions. So I'm going to fit the ridge regression, and I'm going to plot it. So what is being plotted here is, you remember there was a lambda value. Lambda value is the importance you place between minimizing on sum of square errors to simplicity, right? When lambda is 0, it's saying that only sum of square errors is important. When lambda is large, you are saying that simplicity is more important. Okay, so what is being plotted here is log of lambda. Okay, log of lambda. If it was a 10 base log, it would say that lambda of 2 would be log lambda 2 would be 10 to the power 2, 100. This is 10 to the power 4, 10 to the power 6, 10 to the power 8, 10 to the power 10. So you are exploring really large values of lambda. Okay, and this is the log scale. So it looks on linear on the log, it looks linear. Okay, you are exploring a wide range of lambdas, and for those wide range of lambdas, you are plotting here what is the value of these coefficients. Okay, how many features did we have? I forgot, sorry. We have train 14 variables. Okay, 14 values we had, and so I'm plotting beta 1, beta 2, beta 3 all the way till beta 14. That's what is being plotted. When lambda was small, the value of these coefficients were all this number. Some coefficients had a value of, this coefficient had a value of 60, this coefficient had a value of minus 40, and some values in between, whole bunch of values in between. As I started increasing the value of lambda, I'm saying I want simplicity more. So I'm going to increase the value of lambda. When I start increasing the value of lambda, what's happening is, even though there might be a value of coefficients for which sum of squares will be very small, it doesn't pick that. Instead, it tries to minimize the combination of those two. Okay? So what happens is the value of coefficients starts dropping. Okay? The value of coefficients start dropping. When I go to really large value of lambda, the value of coefficient almost goes to 0. It's almost like, no model at all. I'm just going to give mean of y as the best model, which is what we did in the Kingfisher example. No predictors at all. We are just going to use only mean as a predictor for that. That is where this part is going. Okay. So as I increase the value of lambda, I'm starting to go towards simpler and simpler model. But when the lambda is this large, it basically gives up and says, you know what, all values need to go to very, very close to 0. But if you expand it and see, you will see that the values are actually not 0, but it's very small value. The only time all those values become 0 is when lambda is infinity. But practically it becomes 0 at really large values of lambda. You understand what this thing, right? This is what we built our model for. We're saying that as lambda value increases, the value of the size of the coefficients needs to drop. This is ridge regression. Now let's see what happens with lasso regression. In lasso regression, we are not using square. We are using absolute value of coefficients. It's not sum of squares that I want to minimize. Absolute value of coefficients, sum of absolute value of coefficients I want to minimize. Even here, it's exploring different values of lambda. Okay. What's being plotted is log lambda. So this is, if this was log of 10 base 3, it should have been 10 to the power minus 3, lambda of 0.001, to all the way to 10 to the power 4, which is 10,000. So a wide range of lambdas it's exploring. Let me finish this and then come back and clarify that. So this is log of lambda, and just as before, we are plotting different coefficients. When lambda value is small, the coefficients are really large. And what happens as you keep increasing the value of lambda, ridge regression decides around this point of lambda that, you know what, I am going to set the coefficients on the top to be exactly equal to 0. It tried reducing, and at some point it just decides to set it to equal to 0. This coefficient at this value of lambda, it just set it exactly equal to 0. You keep increasing at this value of lambda, pretty much all features except this one, the coefficient is 0. You know what this is doing? It's doing feature selection. By increasing the value of lambda, it's dropping, saying that this feature is not important. If you want to minimize that whole thing, this feature is not important, I'm going to drop it. As the next value of lambda, it's going to drop the next one, and it's doing feature selection. Depending on the value of lambda, you have a way of doing feature selection. And you know what? This feature selection is very different from step AIC. What you had to do for step AIC was you were taking different combination of features and doing regression several times to do that. This is one attempt, one shot. you are able to find, based on a particular value of lambda, what set of features need to be dropped, what set of features can remain. It's a very powerful technique, and this works great when you have million features. When million features, there's no way you'll be able to run it, do step AIC with any reasonable time, right? Your projects will be like typical software project, extend, extend, extend. This allows you to do it at one shot. Do you see the difference? Yeah. So 14 features. So these are all different coefficients. This is, oh man, I hate the resolution on this. So bottom one, the last one is the coefficient 10. You guys can read see my mouse, right? The last one is 10. This is 7. This is 6, 11, 13, and a bunch of them are over here. And as you increase the value of lambda, the first one to go down is one of these guys. I can't tell which one is it, but by 6 goes to 0 around this particular lambda. So depending on lambda, you will be able to do feature selection. You can choose which one you want. Yeah.
So between SAC and the way they work is very different. But
Absolutely.
so is it okay to assume that the outsources, the kind of feature selection, the way they think that this is the most important, that would be similar, or can it be very different?
It will be very different. It can be very different. Why? Step AIC tries to work in trying to drop which one is needed depending on how it's coded. Okay, stepwise regression depending on how it's coded. Like if it is done with p-value, it'll be dropping one set of features one way. If it is based on AIC value, which is what we do in R, it'll be dropping features in one kind of way. What we do here is we are not looking at measuring least squares at all. We are measuring the combination of both of them together. Okay, so both of them do feature selection, but there is no assurance that the features that are selected by step AIC will be the same as here. What we find by experience is that on test data, regularized regression works better than stepwise regression, generally speaking. Okay, if the problem is simple, step AIC is fine. You can do it multiple times and you do the job. Regularized regression typically is people do when large size problems, when this method assures you stability.
But it also will be applicable for like small set of features as well.
It's also used for small set features as well. So this is doing feature selection. This is a good time to emphasize the difference between what we did with PCA and what we are doing here. PCA, we didn't use the term feature selection. What is the term we used? Dimensionality reduction. Final problem that you are going to solve, that you are going to feed into this, multinomial regression or whatever. It's not a problem with 13 variables. It's going to be a problem with 5 variables. But that 5 variables had information about all the features. Okay, it was dimensionality reduction. The size of the problem that it's solving is 5-dimensional problem. What we are doing here is feature selection, where you are choosing which feature is needed based on the Y value, which performs well on that given Y. So there's a subtle difference. When we did for PCA, we didn't pay attention to the Y value at all. We were focusing only on the X value. Here we are making that choice, for this Y value, what are the best ones that we need to pick? And lasso regression allows you a way to do feature selection, to drop off some variables which are not potentially needed. Yeah.
After doing PCA, to what extent we can have another round of reduction in the features if we do either of these two exercises?
So there is this PCA regularized regression as well. Okay, where people have done PCA and then do regularized regression and all that. We are not going to talk about that. I'm introducing you these ideas. What I'm giving you is different tools. You decide for your problem which set of tool is needed and whether you need a combination of tools to do your problem or a single tool will work for you. That's something that you have to decide. Okay. By what I'm giving you is different tools for handling this thing. Yeah.
What I've noticed in playing around with data is that really your feature selection, whether it's PCA or even, in fact, I would get to good apply to this, is the training data set that you have. Like, by varying the set need itself, you get different variables.
Correct.
Or you end up with different variables. How, practically, how would you approach that problem?
So this is, you have raised a good point. By varying the set seed, you get different train variables. You are referring to it as a problem, right? I say that's the strength. That's exactly what the philosophy behind cross-validation is. What you do is you pick different train sets. You train it with different sets and check it on different sets. Each time you measure the error. When you take 10 different train sets and 10 different test sets and you're measuring the error and take an average, now you have a much better estimate of error and now you have a much better confidence in your model because now you know that your error cannot vary more than this. Right? So to me that's actually a strength. The idea that you can take multiple trains, and in fact that leads us to how do you choose lambda. How do you choose lambda is in the train set you do cross validation. You divide your train set into 10 pieces, take 9 of them as train and the last one as validation, train and measure the error on that. Then take a different 9 and different 9. Each time you measure the error. Find out how much is your error for this value of lambda. Then pick a different lambda and again you do it. Each cross validation you vary lambda and find out what is the final error in the validation set. And based on that you choose the lambda that is appropriate for that problem. Which is obviously painfully hard thing to do. Take your train set, divide it into 10 pieces and do it. Which, one of the nice things about life is now you have a way to automate it. Here is the Y value that you are trying to model, which is the revenue generated by that particular kid, that household. We showed it to you. Yeah. So Y is customer data of revenue generated. Yeah. So here is the cross validation of GLMnet. What it does is given the train set, it divides it into 10 pieces, picks 1 9, trains it, measures the value on the test, picks a different one, keeps doing it 10 times and say that for this lambda, the average of all of this is the error. Next, it picks a different value of lambda and again does that. So it keeps doing for different lambdas and what you get is this. I'm going to plot the output of the cross validation. Here are the different values of lambda and what is being plotted here is the mean square error. This is the mean of each one of those validation sets. There were 10 validation sets, right? All of them averaged out. What is the error? That error, it's marking. Okay? And what you see is when the lambda value is small, what do you expect? When lambda value is small, you are minimizing, you're focused only on error. You are not focused on simplicity. When lambda value is large, you are less focused on error, you are focused more on simplicity. So what happens is as lambda value increases, you do expect the error to go up. All of this is on your trained region. You do expect the error to go up. So it does cross validation and with different values of lambda and it's plotting the different values of error. And it gives you a lambda value. This is the best lambda value which optimizes everything at the right level. the right level of bias versus variance, it gives you a value of lambda. So this is the lambda value it recommends. The authors of the package, any of these recommendations, are just like mean, has some uncertainty around it. So there is always some number and a standard error around it. This is the minimum lambda, the best lambda it recommends, and this is another lambda which produces error within one standard deviation of it. So any value of lambda between these two is a reasonable choice. So lambda between -2, log of -2, log value -2 to log value of 0.25, any of those lambdas are reasonable values of lambda. You can choose. How do you choose? 1 second. You might choose to do it by looking at this in combination of old chart versus this. This chart says we pick value between -2 to around 0.25. That's what it recommended, right? Any of those values are good enough is what it suggested. When I chose -2, looks like all of these features are still there. When I choose this, maybe some features have disappeared. It looks like only 10 of them are around here. Originally there were 13 features. By the time I come here, only 10 of them are there. So you know what? If I want a simpler model, I can choose this one. That's still within your acceptable regime. Okay. So I don't know how in the lab you can experiment with it. You can choose the lambda minimum. The output it shows as lambda minimum, and that will be this number. You can experiment it. It will give you lambda minimum and lambda 1 standard deviation. You can experiment with values in between and find out which one does well for your test set. And based on that, if you want simplicity, you'll choose a larger lambda. If you are focused more on error, whatever, you might choose the smaller lambda. But this is the way the process is done. And what is inside this process is this whole concept of simplicity. Number one, that is plays a very key role in it, that bias towards simplicity. And one benefit that comes along with simplicity is that it also helps you solve for cases where the original linear regression is ill-defined, where it's singular. It regularizes that original problem. So where is that problem? Where does it happen? When you have large multicollinearity, high level of multicollinearity, linear regressions can have a problem. Other place where it's a problem is when the number of features are very large. Problems where you get a small data set in terms of number of records, but large number of features. In those problems, again, regularized regression does a great job. So you have two options, ridge regression or lasso regression. Ridge regression does not set coefficients to 0, but it just reduces the size of the coefficient. But it has its same impact on the test set. Test set, the performance is stable in ridge also. Lasso, performance is stable on this thing, but it has an added advantage of reducing the number of features. So it can be used for feature selection. Instead of step AIC, I would recommend you to use lasso regression if feature selection is important. Let me go back to the presentation. I have, yeah.
Can we blindly replace step AIC with this lasso in all our analysis activities?
It's depends is always the answer. These are all tools that work well in some situation. The statistical analysis, what lot of experienced data scientists say is many of the real world problems, regularization works much better than step AIC. But that doesn't mean that in the specific problem that you are doing, that it will do better than step AIC. There's no guarantee of that. As I said before, these are different tools, and you might find one tool works better for you versus, in your case. Yeah. Dying.
I definitely need to go back and just
Insomnia, huh? Yeah. This is for ridge regression for lasso. Yeah. Yeah. Okay, thank you. Thank you. So your question, how do I know? Yeah. Correct. So, good point. You don't know how much information you lost. However, you don't really care about how much information you had. You care about the philosophy with which this approaches is that maybe a variable had a lot of variations, but if it's irrelevant to explain my why, I don't care. That's the approach this is taking. It's just keeping for explaining my why, how much do I need, is the attitude this one takes. PCA takes attitude that I don't care about why, I want to find out which variables have least variation and I'm going to drop it. That's the approach PCA takes. Both of them have their strengths, both of them have places where they are used. There is no universal answer of this is the best method, this one won't work. In the case of my example, PCA works very well. So that's what I use. In examples, in other examples, people use regularization more frequently. And as I said, there are I saw several recent papers where they do PCA first and then they do regularized regression as well. But that gets like too many tools, and I don't know whether I'm doing overfitting in a new way. It's hard to make sense of that particular, whether are you doing too much or too little. It's hard to make sense of that.
But I think to this point, the rule of thumb is if you need interpretability, then you stay away from
Absolutely. Absolutely. If interpretability is important, then you would stick with interpretability is important, and you want feature size of the problem reduction, then lasso is your answer. If the question is you don't care about interpretability, I want the smaller problem and keep only relevant information, PCA does a good job of it. So when do you do ridge? Why would you do ridge at all? Ridge does not do feature selection, okay? But ridge does very well when your values have multicollinearity. You remember this particular problem. In this particular problem, where I said there are infinite possible combinations, and I asked you to do, beta squared, beta 1 squared plus beta 2 squared. I mean, of all of these infinite possible solutions, which one minimizes beta 1 square and plus beta 2 square? We did this, right? For this particular problem, we chose this answer, x1 plus x2, where both these features are there. That is what minimizes this number. Any of the other guys, it doesn't minimize. But instead of trying to minimize this, if I try to minimize absolute value of beta 1 plus absolute value of beta 2, if I try to minimize this, you know what I'll find? This one, summation of these two is giving you 2. This one also gives you 2. 2 times x2, that will also give you 2. So it's not clear. What ridge does is it arbitrarily picks one based on how it initializes the code. It arbitrarily picks one. Okay. Sometimes it might be desirable, sometimes it might not be desirable. In life, nothing is like pure good or pure bad, right? You look at it based on that particular situation and finds out what works for you. So every single of these methods it's important to understand what is the pros and what is the cons of each method, and then use it based on that. But all three of them are regularly used. Okay, it's funny, regularly used regularization methods. So I've talked about a little bit about why lasso leads to sparsity, but I'll skip that explanation and move forward. What I've summarized here the advantages of ridge and lasso. Everything that's here I've already talked about. Please do look at it later. Now, so why choose only one? You have two methods. Why not use a mix of both of them? Right? So elastic net does that, and GLM net functionality allows you to choose a linear combination of both ridge and lasso. So this is your sum of square errors. This term is what you put in your, which one is it? Lasso. This one, ridge. So there is a parameter alpha that you can provide, which will give you, that value of alpha is anywhere between 0 and 1. When it is 0, it does a ridge, and the other one it does lasso. Actually, it's the other way. It's coded the other way in R. Yeah, but in R, when the parameter is 1, it does lasso. And this thing, I'll change it on my presentation. So this parameter alpha that you see here, it when you set the parameter to be say 0.5, then it effectively uses a combination of those two. That's called elastic net regression. Okay, so it uses part ridge and part lasso, and that's what people do when the problem actually has strong multicollinearity, and they suspect that a lasso might not do great, so then they use the mixture between lasso and ridge together. I believe so. But when you mean everything, you're referring to PCA, this?
Whatever we discussed this morning.
Yeah, and more. we are going to have one more topic to cover today. Yeah. Yeah. Yeah.
With that alpha value be between 0 and 0.5 or 0.5 and 1.
Yeah. You can choose any of the alpha values, and the way people normally choose is again use cross validation to decide what is valid for your data set.
Instead of using these three values of alpha,
Yeah.
can we use
Any other values, any combination is fine.
So in that case, which type will it be used?
So it tries to minimize this equation altogether. Instead of trying to solve this problem and solve this problem and give an average of those two, it doesn't do it that way. It tries to, so minimization problems are solved using one particular function. Okay, there is I don't know whether we are covering minimization problems in any modules or not. It's a very basic mathematical methodology where you have a function and you're trying to minimize that function. I mean, entire calculus was developed because of minimization ideas. So there are several functions that have been written, several methodologies that are there to minimize any given quantity. What is used inside elastic net problem is you give the function that needs to be minimized, and it will happily give you the coefficients that minimizes it. So what goes in is the combination of these two goes inside that particular function, and it does the minimization on the whole. So yeah, but it's a very standard numerical analysis method. Nothing deep on that. Yeah. There are pluses and minuses. None of them are at a level that we need to worry about at our initial data analytics level. There are always some exceptions under which this particular method works best and no other method works. But in a standard this thing, most of these methods work reasonably well. Any of the regularization methods work reasonably well. Okay, this is something you will explore today in the lab. Moving on to the next topic, which is naive Bayes algorithm. Fortunately, this is a simple topic. So simpler topic. Actually, it's very simple topic. It's it won't take that long for us to cover this. Do we need a break before that, or?
No.
Yeah. Okay. Because we have only half an hour left, so let's rush through this. Now, we talked about logistic regression yesterday, where we were trying to make, given some set of features, how do you decide which bucket this set of features applied was best applied to, right? That's what we discussed. But there are plenty of classification problems where the number of buckets that you have is large. Okay, plenty of them. For example, given an article, you need to predict in which section of your newspaper does this article go to. So you look at the article, you read all the words, analyze the word frequency, and based on that, can you decide whether it needs to go to the current news section, international news section, arts, sports, or fashion? This is a kind of problem that gets solved every day in any of these news aggregation sites, right? Google News or whatever be the news aggregation site, they solve this problem all the time. So where the number of categories that you have is clearly more than 2. Another one is, given a photo of a car number plate, identify which state it belongs to. So image analysis problem. This again happens all the time. You pull your car to any toll gate, they take a picture of that, and that picture looks at each character and it separates out the character and compares this pattern of this character, which category does it match to, which of those 26 alphabets does it match to, and based on that you allocate it to one particular state. Again, a categorization problem where there are multiple categories that are there. And if you have used Shazam or any of the other music identification apps, it looks at an audio file, look at these features and try to identify which genre it belongs to, and particularly which song it belongs to after you identify the genre, right? So all of these kinds of problems involve dealing with multiple categories. Logistic regression is does a poor job in those kinds of situations where you're dealing with multiple target categories. Is there a better method? Okay, so better method exists. What we did in logistic regression is the following. Although we didn't talk about these classification problems as conditional probability, all of them were conditional probability problems. What did we do in logistic regression? Given set of features, you wanted to find out the probability of it being in that particular class, right? That's exactly a conditional probability. Given this X matrix, what is the probability that this X matrix belonged into Y? That's what we were evaluating, right? The way linear regression solved this problem, logistic regression solved this problem, is you assume a relationship between X and your Y. Remember the sigmoid curve? We assumed this particular relationship, and then we found parameters that fit in that particular relationship. That's what we did, right? This is one way of solving the problem, and this kind of models are called as discriminative models. There are different set of models. Yeah.
Why do you think that the logistic regression does a poor job?
I'm telling out of practice. that when you have these large set of classes, it's not necessarily the best method that is there. That's all. It's not obvious that it's going to do a poor job, but I'm telling from practice, from experience. So, thing is, ultimately we are solving a conditional probability problem, right? You guys remember the Bayes rule, which allows you to find one conditional probability based on its inverse probability. So that's another way to solve the same conditional probability problem, where instead of, this is the one that you are trying to solve, but you might be able to easily compute this one. So let's compute this one, and from this, using Bayes relationship, we can evaluate this one. Okay, this kind of models are called as generative learning models. Previous one was called discriminative models. These are called generative models. It looks like you're computing something that is completely different, but we know through Bayes rule that these two are related, and that's what we are going to do. At this point, it looks very abstract, I know, but it will be clear once we start doing an example. The example that we are going to be picking on is an example, a data set which contains the voting patterns of members of Congress, the US members of Congress from 1984. The Congress at that point had 435 different congressmen. There were two parties, so every congressman is either a Republican or a Democrat. Okay, so Republican and a Democrat. So what's listed here is they have removed the names of the congressmen, and they are giving you data of which party each person belongs to. So each one corresponds to one particular congressman, and they have the voting record for 16 different issues. This was collected over a span of, I don't know, 6 months, and there were 16 different issues that came up for vote, and in each issue the congressman voted in a different way based on his particular party affiliation, based on his own principles and all of that. That person made these votes. So this is the issue number 1, which happened to be providing funding for, in some way, for handicapped infants. Issue number 2 was some water project cost sharing. Issue 3 was voting of budget resolution. A bunch of these things were there, and they are, what you listed here is whether that particular person voted no or voted yes on each one of those issues. You'll also notice that for some of these votes you see NA. NA typically means that that guy chose to not vote.